Welcome back, everybody, to another lecture of Aero 3240. Yes. Okay, so last time, what did we do? Well, we looked at the derivations of the Gauss variational equations that essentially gave us a way to analyze the effects of any kind of perturbations onto the orbital elements. And specifically, all we needed to achieve the work was the x, y, z components of our perturbing acceleration as seen in the orbital reference frame, right? These were the FR, F theta, and Fz. And then all you have to do from there is plug these back into the GVEs to figure out the rate of change in our orbital elements. Now, this is a very generic tool that, again, allows us to analyze any kind of perturbations. But today what we want to do is to look specifically at a case of low Earth orbit, or LEO for short, where the main perturbing acceleration comes from the non-sphericity of the Earth. Because in practice, the Earth isn't a perfect sphere, but is rather an oblate shape. So think of it as a football, essentially, more or less, where the radius along the poles is about 40 kilometers less than the equatorial radius of the Earth, okay? So that deviation causes some perturbing acceleration from the perfectly spherical model. And this causes the spacecraft to accelerate differently when it is over the pole versus when it is at the equator, okay? So today we're going to derive the perturbing acceleration due to this non-sphericity of the Earth, and then use that result and plug it back into our Gauss variational equations to understand the net effects of that specific perturbation, which affects any spacecraft in low Earth orbit on the orbital elements, okay? So that would be section 3.2.1, non-spherical primary body. I think I'll have to switch to another color for the entire lecture today because the black marker is not working well anymore. So let's use green. Okay? To start off this derivation, we have to go back to the inertial acceleration of our spacecraft with respect to the primary body. And turns out that this inertial acceleration could have been obtained by taking the gradient of the geopotential function u. Okay, so remember for the two-body problem, the inertial acceleration is minus mu times r vector over r distance cubed, okay? And we had derived that from Newton's laws. But another way to derive an inertial acceleration in a gravitational field would have been to take the gradient operator and apply that to the geopotential function u. Now, the gradient operator turns out to be the partial derivative of any function along the x unit direction, y unit direction, and z unit direction as well, okay? So for a Keplerian orbit, or an orbit which is only affected by the primary body, this is a synonym, Keplerian orbit, our geopotential function u is actually simply mu over the distance between m1 and m2. So if you were to take the gradient of this geopotential function, then you would obtain, obviously, your minus mu r times r vector. As simple as that. But here we are not dealing with orbits that aren't affected by perturbations anymore, because we got smarter because we started chapter 3, right? So instead of considering this very simplistic geopotential function, which is simply mu over r, we will consider an arbitrary shape that is creating this potential function such that u is going to be obtained by mu over r, but this times a double summation from degree n ranging from 0 to infinity and then summation of order m equals 0 to m equal n, or the order equal to the degree of what? Well, of this constant, which denotes the mean equatorial radius of the Earth, 6,378 kilometers, over the current distance between the spacecraft and the primary body, that now has a very generic shape that is going to be defined through the selection of the coefficients in this double summation equation, as you will see in a second, to the power n times p of degree n order m, which is function of sine of the geocentric latitude phi. I'll draw a figure in a moment to show it exactly what this variable represents, and times cnm, which is a geopotential coefficient, cos of order m that multiplies the longitude, plus another geopotential coefficient, SNM, that multiplies sine of m times longitude. Okay? So essentially, if you would like to generate a very accurate potential field of an arbitrary shaped gravitational primary body, then you could very well perform the double summations all the way to degree and order, say 100. And that would give you a very accurate effect of the primary body attracting the spacecraft, depending on the current spacecraft distance from said primary body, and depending on the actual primary body internal mass distribution, which is quantified through those geopotential coefficients. Okay, so those are very specific to the body about which the spacecraft is orbiting, obviously, but also not only depends on the current distance between M1 and M2, but also on the current geocentric latitude and the current longitude. So all this to say that based on the current spacecraft position with respect to the primary body, the spacecraft will experience a different geopotential field, U, and then by taking the gradient, we'll then experience a different acceleration. So we talked about all the terms of that double summation equation, but this one, which is a Legendre polynomial of degree n and order m. Okay, so this is a mathematical object which is defined in the literature. So for degree n and order m, there are analytical equations that will provide us this term here. And those here are provided through satellite observations that are orbiting about the primary body. So those are scientific satellites that are designed specifically to figure out these geopotential coefficients. So over the years, as more and more scientific satellites are being designed for this very particular purpose, those coefficients are going to become more accurate, okay? So for the mean equatorial radius of the Earth, in this course we're going to assume that this is 6,378 kilometers simply, okay? So the Legendre polynomial, I'm going to give you the mathematical definition. polynomial. So this is P of degree n, order m, of some arbitrary function. Now just keep in mind that that arbitrary function in our specific situation here happens to be sine of the geocentric latitude, but generically speaking, this can be obtained by 1 minus the function of interest, x squared, to the power m over 2, then the derivative of that function to the power m of p n that depends on the function x. Okay? Now, this can be somewhat complicated to figure out, so to ease up the follow-up developments, I'm going to give you exactly the results for degree 0, order 0 of some random function x, and the answer for this one is easy. It's always equal to 1. Okay? Now, if you have Legendre polynomial of degree 1, order 0 of some random function x, this is just going to be the function x itself. If you have p degree 1, order 1 of function x, the answer is going to be 1 minus x squared, and you're going to take square root of that. Then move around here. Now if you look at Legendre polynomial degree 2, order 0 of function x, this is going to be 3 over 2 times x squared minus 1/2. And then you can continue with the process and pick up any mathematical textbooks and figure out the other Legendre polynomial functions here. Okay? But for our purpose, those 4 will be sufficient for us. So we don't need to go any further than that. Because, again, our objective here is not to get the most accurate geopotential function of the Earth that we can think of. We're going to let this to folks at NASA and at the Canadian Space Agency and organizations like that. So here in the context of this course, all we'd like to know is the biggest gravitational contribution in terms of perturbing acceleration on our spacecraft. So to do so, let me first talk about the geopotential coefficients. That are CNM and SNM. So whenever we look at those coefficients and we look at the order equal to 0, then we're going to refer to those as zonal coefficients. Right? Because whenever we plug m is equal to 0 in those geopotential coefficients here, we're going to get sine of 0, which turns this to 0. And then here we're going to get C and 0 cos of the longitude of, well, just 1 actually, because cos of 0 is 1. Which means that the geopotential function u, whenever we assume that m is equal to 0 for our geopotential coefficients, is going to express the dependence on the spacecraft position in terms of geocentric latitude only on the potential function u. And turns out that the dependence on the latitude on the gravitational field that the spacecraft is experiencing is known as a zonal contribution, and therefore the particular coefficients that we consider at n equals 0 are going to be referred as zonal coefficients. And And common practice is not to use then CNM, where m is equal to 0. So in that case, we're going to say that CN0 is going to be simply referred to as minus j of m for whatever reason, okay? Maybe to ease up the nomenclature a little bit, I don't know. Or in other words, we're going to say that the negative of any zonal coefficients is going to be equal to j of degree n, okay? Turns out that this is important for us because, again, we're not seeking the most accurate analytical expression to describe the potential field of the Earth. That would just be too much for the context of this course. So what we're going to do next is to limit ourselves in terms of evaluating the double summation expression to degree equal 0, 1, and 2, and order of 0, such that all we're going to end up with in this double summation are zonal coefficients. All right? Now let me first go back to what I said previously, which is the geocentric latitude. So let me define it graphically so that you understand the difference between geocentric latitude and geodetic latitude. Those are two different things. So it is important to specify which one of these are we talking about. So now that we are considering that the Earth is an oblate sphere, okay, this is highly exaggerated, of course. Looks like a potato, but it's not a perfect sphere. So here you have IZ, the inertial reference frame, and the equator here. So the geocentric latitude is, if this is a spacecraft, here out there, coasting along its orbit around the Earth, then you know that you have this position vector r, which goes from the center of the Earth all the way to the spacecraft. So this is the geocentric latitude, defined by the angle between the equatorial plane and this guy, such that we refer to this distance between the center of M1 all the way to the spacecraft as the geocentric distance, okay? So up to this point, I had only referred to it as distance, but the technical term would be geocentric distance because this is from the center of the Earth, and hence geo for Earth-centric center, obviously. But the geodetic distance would be the distance from the spacecraft going down in a perpendicular fashion to the surface of the Earth immediately below the spacecraft. Okay? Just keep going on with this line here. And that distance would be the geodetic distance. And related to geocentric distance and geodetic distance, there are also geocentric altitude from the surface of the Earth here all the way to the spacecraft along the blue line, and the geodetic altitude from the surface of the Earth to the spacecraft but along the green line. Okay, so don't confuse the two, especially when we talk about altitude. Geocentric altitude is following our good old position vector, whereas geodetic altitude is measured perpendicular to the ground below the spacecraft. All right, so this is the angle that we're going to need in this double summation expression here, which is the geocentric latitude. So if this is equal to 0, it means that the spacecraft is hovering over the equator. If it's pi over 2, it means that the spacecraft is over the pole, and so on and so on. Good. So again, we're going to limit ourselves to degree equal to 0, 1, 2, and order exactly equal to 0, which will then simplify our geopotential function for an arbitrary degree and order to be equal to summation of n equals 0 all the way to 2. And here we don't have a summation anymore because this is n is equal to 0 and remains at 0. So we're going to have our equatorial, our mean equatorial radius of the Earth. That's our 6,378 to the power n. Pnn is our Legendre polynomial of n and comma 0 because we are fixing our m to be equal to 0, which is function of sine of our geocentric latitude that then multiplies c n 0 cos of 0, which is 1, plus sine of 0, which is 0. So that's all we have here. Okay? Which means that we can expand this summation into 3 different terms and write that whenever n is equal to 0, we get mu over r times 1 times p 0, 0, function of sine of our geocentric latitude, times c 0, 0, plus, I'm going to leave the mu over r outside, okay, just to simplify my life, plus mean equatorial radius of the Earth over r to the power 1 times p 1, 0, function of sine phi times c 1, 0. And lastly, the third term will be plus r Earth or r distance to the power 2 times p 2, 0, function of sine phi times c 2, 0, and then close this bracket here. Let me see if I got this right. Yes, that looks about right. Okay, so I haven't told you what the geopotential coefficients were for different degrees and orders. So let me do that for degree 0, 1, 2, and order m, which is what we are concerned about, because we said that we're going to make our geopotential function a bit more accurate than the two-body assumption, yet not as accurate as, order 100 and degree of 100. That would be just too much for us, okay? Too exhaustive. And of course, this is all equal to u. So we're going to say, let me give you what the geopotential coefficients are. So C 0, 0 is actually equal to 1. Yeah, we like it. It's easy. C1, 0 turns out to be equal to 0, which is great. And then C2, 0 is equal to minus 1.08 264 10 to the negative 3. So that means, as a heads up, that, as you will see later on, that the potential perturbing acceleration due to the fact that the Earth is slightly oblate and not a perfect sphere, the perturbation is actually 3 orders of magnitude smaller than the two-body acceleration, essentially, which is what we'll see eventually. So it is a small perturbing contribution, yet this is worth considering for low Earth orbit, because that will mean that only the small effect that has a power of 10 to the negative 3 is going to be able to shift our orbit slightly, or shift the orbital plane and also shift the orbit within the orbital plane. So we're going to see that later on, okay? But these are the constants for our geopotential coefficient C for degree 0, 1, 2, and order of 0, okay? Because this is what we need in this expression here for our geopotential function u. So let's plug this back here to get mu over r. Yeah, let's leave the Legendre coefficients as they are now. This function of sine phi, C0, 0, good news. This is 1, plus your C1, 0 is 0, so that cancels this term altogether, plus r Earth over r distance square p to 0 function of sine phi. And I'm just going to rewrite this constant as c to 0 for now, because I don't want to keep playing with this numerical value all over again. But this is what we get. Now let's go back to our Legendre polynomials, and specifically degree 0, order 0. And if you remember, for an arbitrary function that was x, I had told you that the answer was just the function, was just 1 actually, for 0, 0. That remains the same. We don't need the, do we need? No, we don't need P1, 0 because this term got cancelled by virtue of this geopotential coefficient be driven to 0. So all we have to look at now is P2, 0, and our function is sine phi. And that's our 3 over 2. Previously it was x squared, so now it becomes sine square phi minus 1/2. Okay? So let's use those specific Legendre polynomials whenever our function of interest is sine phi, and not some just random function x, to come in here and rewrite the whole thing as mu r. This is just 1. So that works out. Plus our Earth over our distance square times 3 over 2 sine phi square minus 1/2, like this, times c to 0. Okay? Or alternatively, what you can do is swap out this notation for the J notation I had talked about, right? C2, 0 is actually equal to minus J2, okay? And this is why we are talking extensively in astrodynamics or orbital mechanics about the J2 perturbation. So the J2 perturbation is the contribution to the Earth oblateness effect onto the gravitational attraction, okay? Because of this factor that remains inside our geopotential function at the end of the day. So this is what J2 is, okay? Gravitational perturbation due to a non-spherical primary body. So inserting that notation in here, I can then come in and write that my geopotential function will be mu over r, open the brackets, 1 plus r Earth over r square because there's a negative sign, I'm going to apply the negative sign to everything here. So times 1/2 minus 3 over 2 sine phi square. Close this, and don't forget to insert the J2 coefficient in front of this. And because do I want the 2 there? Yeah, I can factor the 1/2 here and just clean that expression a bit. Write that would be J2 r Earth square over 2 r square. That multiplies 1 minus 3 sine square of our geocentric latitude phi. I'm going to stop here for the geopotential function, okay? Now, if you look closely, what you see is that your net geopotential function is actually the geopotential function for the two-body problem, which is just this term here, your mu over r. Remember our initial discussion on geopotential function for the two-body problem being just mu over r, and then taking the gradient of that, you would get what you know for the two-body acceleration, which is your minus mu over r times r vector. So we have the two-body contribution here, plus mu over r that multiplies the second term. So plus the geopotential function being contributed by the J2 effect, which is the oblateness of the Earth. Okay? Or alternatively, you could say that geopotential function due to J2 only is going to be equal to mu over r. Yeah, so this times that, yeah, times J2, mean equatorial radius of the Earth square. I have my 2 here, and then it becomes r cubed, and this multiplies 1 minus 3 sine square of my geocentric latitude. Okay? And this is the only term I'm going to consider for now. In most research work or practical applications, we don't even go up to degree order 2020, but typically it would go up to J5 maybe for the effects. So this is J2, this is the main contributor. And again, J2 compared to this guy is 3 orders of magnitude smaller. And if you go J3, I believe this is 10 to the negative 5 in terms of relative magnitude compared to the two-body. So that's why it's quite a bit more accurate to consider J2 than just a two-body potential function. Yet it could be interesting to also consider J3, 4, and maybe 5. And after that, the net effects of those higher coefficients kind of drop rapidly. But J2 is definitely a big contributor. Okay, so that's why here we are considering J2, but we're not going any further than that because this is kind of beyond the scope of this course. But for example, in my lab, we typically go up to J5 when we deal with astrodynamics or orbital mechanics. Okay, so are we done? What is the purpose of deriving the geopotential function U due to J2? What is the point? Well, the point was to get the acceleration, the inertial acceleration due to J2 on our spacecraft. and call that our perturbing acceleration. And then look at the x, y, z components of this perturbing acceleration vector related to J2 and plug those in our Gauss versional equations to better understand the effects of J2 on each of the orbital elements of the spacecraft, which will be time varying, as you know. And then we'll also calculate the secular variation and the average rate of change due to J2 specifically onto our orbital elements. And all of this will be done through the tool we developed last time, which is the Gauss versional equations. Okay? So if this is the geopotential function u, I'm going to switch to blue. Again, what we want is the perturbing acceleration vector, but this time specifically due to J2. And for that, all we need to do is take the gradient of this guy, u J2, which means that we're going to take the partial derivative of u J2 along x, and we're going to multiply this with Ix unit direction plus partial derivative of u J2 with respect to y in the direction of Iy, and then partial derivative of u J2 with respect to z along Iz. Now those variables x, y, z actually correspond to the x, y, z components of the position vector r in ECI. So we're going to say r vector expressed in the ECI reference frame through its vectrix is going to be r I like this, with ri being equal to x, y, z scalars that denote the x, y, z components of my position vector r seen from the inertial reference frame. So this is what these variables here refer to, such that this here, my r scalar, is just going to be the Euclidean norm of this column matrix, or alternatively x squared, y squared, plus z squared, and square root of all of that. Okay? So what we're going to do next is to, now that we've established this and what the gradient operator means, we also have to express this slightly differently, because we have to take the partial derivative with respect to x, y, and z variables in this equation. So we know that this depends on x, y, and z. How? Well, through this relationship. This is a constant, 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 but this term is also a function of potentially x, y, and z too. So we have to explicitly rewrite that term in terms of x, y, z, such that we can ultimately be able to apply the gradient operator to this expression, or take the partial derivative of that expression with respect to x, y, and z. Okay? Otherwise, if you have hidden variables behind a term, then the partial derivative you're going to obtain will be wrong. So you have to explicitly write all the dependencies on the variables of interest. And again, in this case, it's x, y, z. So for this, all we have to do is to go back to our definition of geocentric latitude. And this is just 1/4 of the oblate Earth, okay? So geocentric latitude is this angle. This is your position vector from the center of the Earth up to the spacecraft, such that we know that the z component, if this is Iy or Ix, doesn't matter, and this is IZ, looking at the North Pole of the Earth, obviously like that. We know that the Z component, or the component of the R vector projected on the IZ direction is just, in terms of magnitude, is just Z. And the magnitude of this side here is just R, such that when we have sine of this angle, we'll simply replace it with Z over R. Or because here we have sine square, we can square both sides like that. Okay? So with this in mind, I can go back and explicitly write all the dependencies of all the terms in that equation with respect to x, y, z by saying that u j2 is going to be mu j2 mean equatorial radius of the Earth square over 2 r cubed times 1 minus 3, and then I'm going to substitute my z square over r square like this. And furthermore, I'm going to distribute my r square to both of these terms and write mu j2 equatorial radius of the Earth square over 2 times 1 over r cubed minus 3 z square over r to the power 5. Like that. And to do the gradient operator properly, you would have to replace this with square root x square plus y square plus z square, all this to the power 3. And similarly for this one, the same thing, but to the power 5, and then do the partial derivative along x plus the partial derivative along y plus the partial derivative along z. I'm going to skip that step. I'll let you do it on your own, which I know you will, of course, do it. You will, right? I can count on you? Thank you. Okay? So, you may pause the video now and do it. Your new sheet of paper. And now that you've been able to solve it, let's just compare with the answer I'm about to give you, which should be 3 mu j2 r Earth square over 2 r to the power 5, open the big bracket, 5 times r vector dot product iz over r square minus 1 minus, this multiplies r vector, of course, and this minus 2 r vector dot product iz, and this multiplies iz like that. So this is an important result because this, or did I forget the curly bracket? Yeah. And here. Okay? So this result quantifies the perturbing acceleration due to J2 on our spacecraft. Right? So remember when I had written a while ago our equation of motion for a spacecraft orbiting a primary body. That's what we had. Q. I had said, well, you can make it more accurate by adding perturbing acceleration terms like that, FP. What if you only consider J2? You add this big term next to the two-body equation, and that'll give you the net acceleration applied to the spacecraft due to the main attraction of the body, which you consider a perfect sphere, plus the contribution due to the fact that the actual shape of the primary body deviates from the perfectly spherical model, okay? So this is where this expression would be relevant. But that's not exactly what we want to do here. What we want to do was to evaluate the effects of J2 on our orbital elements. And for that, we need to use the Gauss versional equations, obviously, the GVEs. But GVEs work only in terms of FR, F theta, and FZ. Oh, are we stuck? Because in that expression, I don't see FR, F theta, or FZ. So what can we do about it? Well, if what you want to do again is to analyze the effects of J2 on OEs or on orbital elements, all you need to do is to figure out the x, y, z components of all the vectors involved in that expression. In which reference frame? Well, in the orbital reference frame, because this is where we'd see the FR, F theta, and FZ components appearing, okay? So the first vector we have is our position vector. So how can we describe this vector in terms of its x, y, z components in the orbital reference frame? Well, same thing as before. Vector x, orbital, transpose, times the components of this vector in the orbital reference frame. And hopefully you will remember that the x, y, z components of your position vector in the orbital reference frame that has its x unit vector always pointing at the spacecraft as the spacecraft orbits, well, will be r, 0, 0. Okay? Or alternatively, because it is such a simple expression for x, y, z components, we can make our life a little bit easier by expanding what the vectrix here is equal to. So again, a vectrix is a matrix of unit vectors of the reference frame of interest. And the transpose means that this is going to be a row matrix. Like that. If you're not too sure, go back to chapter 1. And this multiplies the 3 by 1 r 0, 0. And all together means that your position vector in the orbital reference frame is going to be simply the norm of this vector in the direction of OX only. So whenever we'll see the r vector in that big equation, we'll just replace it with r times OX unit vector like that. I'm going to write on top of this r vector need to be this simply. What else do we have? Well, we have the IZ. Did I do IZ or it's just too simple? We can do IZ. Okay? So to do IZ in the orbital reference frame, we have to use vectrix related to the ECI reference frame equal to the rotation matrix CIO, taking us from O all the way to I. So remember, this is the first use of a rotation matrix. That is to relate the orientation of, in that case, ECI with respect to the orbital reference frame. Or alternatively, I can rewrite that expression as being equal to, note that here it's not the transpose of vectors, so this is a column matrix filled with IX, IY, and IZ equal to my 3 by 3 matrix that I'll just denote in a very generic manner as CXX, CXY, CXZ, CYX, CYY, and CYZ, and CZX, CZY, and CZZ, times the vectrix for the orbital reference frame, which is going to be OX, OY, and OZ unit vectors, like that. Okay, so what I wanted here, I don't care about what IX is in terms of OX, OY, OZ. I don't care about IY, because this expression only depends on IZ in terms of unit vectors for the ECI. So I'm just going to take that linear expression here and say that IZ is going to be equal to CZX times OX. CZX as a scalar times OX plus CZY times OY plus CZZ times OZ. Okay, so what are these scalar components of this vector equal to? Well, for that, hopefully you have solved problem 1.2 in chapter 1. And if you have done things properly, you should have found that CZX in this rotation matrix that you had solved for in 1.2. So this element here should be equal to sine inclination, sine argument of latitude. So that's for CZX, so times OX unit vector, plus this element here of the 3x3 rotation matrix, taking orbital and transferring it to ECI, is going to be sine I cos argument of latitude times OY unit vector. And finally, the Z component, or the third row, third column entry of the rotation matrix CIO, you should have had obtained cos I times OZ. Okay, like that. And all this is for IZ unit vector. So essentially, just by looking at it, it makes sense, because based on the inclination of the orbit quantified by I and the current spacecraft position quantified by argument of latitude U, you're going to get a different value for IZ function of the orbital reference frame, because the orbital reference frame keeps changing as the spacecraft orbits around. Okay? So that's what you get for IZ. Let me just use S and C for sine and cos, respectively. Sine I, sine U, OX, plus sine I, cos U, OY, plus cos I, OZ. So that's all we have. Although we can also directly calculate what is our vector dot product IZ equal to. And if you remember how to do the dot product of two vectors given their x, y, z components, you'll realize that all you have to do is take the transpose of the components of the first vector times the components of the second one. And if you do so, you will easily realize that our vector dot product IZ will simply be R times sine I sine U along OX. Sorry, that is a scalar, obviously, so no vectors involved anymore. So just this times this. Okay. So all we have to do now is substitute those three things inside this expression and then simplify it, and then looking at the result we're going to get and figuring out what is FR, F theta, and FZ, or in other words, what is multiplying OX, OY, and OZ unit vectors respectively, and then plug this back into the Gauss-Original equation and analyze the effects of J2 on an orbital element. Okay, so this is the process. Yeah, okay, so let's do it. FP J2 vector equal to 3 mu J2 equatorial radius of the Earth square over 2 distance to the power 5. Open a big bracket. Now I have 5 that multiplies R dot IZ, which is this. Wasn't this supposed to be square? Yes. I had forgotten the square here. Okay, apologies. This is equation 3.56 in the lecture notes. There is definitely a square term that goes there. I just missed it. Okay. So that is R sine I sine U square divided by R square minus 1. And all this is what multiplies R vector. And R vector is R magnitude times OX unit vector, like that. Minus 2. 2 times what? Well, 2 times R dot IZ. So 2 times R sine I sine U times IZ. My IZ has components along X, Y, and Z of the orbital reference frame. So I have to take all those into account. So sine I sine U along OX plus sine I cos U along OY plus cos I times OZ, like this. And close the big curly bracket here. What else can I do? Well, turns out that this term and that second one are both multiplied with R here and here. So I'm gonna factor this out. And see what we end up with, okay? I'm going to use the magic of the board, i.e. I'll just erase terms and keep moving forward instead of rewriting that equation over and over again. So feel free to pause the video whenever you feel that you need to write down the next equation and take your time. But I'm going to go rather quick here because I have, again, access to the eraser. So this R term is being factored out, this R term as well, such that this R to the power 5 becomes R to the power 4. Now I have this R square, while R sine I sine U, all this being squared. I'm going to square individual components. Sine I square, sine U square, and then cancel the R squared terms. And just keep sine I sine U square, so sine I square sine U square minus 1. Okay, Furthermore, here if I only focus on this, I have 2 sine I sine u times OX, which is 2 sine I squared sine u squared times OX, which is exactly what I have here. So 5 minus 2 is going to give me 3. So 3 sine I squared sine u squared minus 1. So this has been taken care of. And I am left with 2 sine I sine u, sine I cos u OY. So 2 sine I squared sine u cos u along OY, and minus 2 sine I sine u cos I along OZ. Okay, so let me just rewrite it on top here. I know it goes a lot faster when you have the magic of the board available to you, which you don't, but that's okay with me. Two sine I sine u cos I OZ, like that. Sine I cos u 2 sine I cos I. Great. So what I'm going to do next is to use a trig identity that tells me that 2 sine u cos u and 2 sine I cos I are actually respectively equal to sine 2u, and here sine of 2i, like that, okay? Such that I can go and replace this with minus sine of 2u, and I have the sine I square that is still there. And here, let's not forget about the sine u that I have. So minus sine 2i times sine u times OZ. Great. This is so fun. Isn't it? Yes. Okay. So now that we have everything we need in order to figure out FR, F theta, and FZ, the answer is yes, we do. Because what is FR? Well, FR is the x component of your perturbing acceleration, or if you will, the component along OX. I can clearly see my component along OX because this is what multiplies OX. F theta is the component of my perturbing acceleration vector in the direction of OY. And here I can clearly see what I have multiplying OY, so that is my Y component. And FZ is the component of my perturbing acceleration in the Z component, or along the Z component of the orbital reference frame, or whatever multiplies OZ unit vector. Obviously, all those three will get multiplied by this factor, but just by inspecting this relationship, I can now extract manually FR, F theta, and FZ out of it. Okay? So we're going to say that FR is actually, just for fun, I'm going to flip the sign of whatever multiplies OX such that I end up with negative for the OY and negative for OZ, but also negative for OX, just to be consistent in terms of the signs. But I could have left OX being positive, it doesn't matter. So I'm going to write minus 3 mu J2 mean equatorial radius of the Earth square over 2 R4, and because I've decided to use a negative sign here, I need to flip the order of this parentheses and write 1 minus 3 sine square of inclination, sine square of argument of latitude, right? So this is a scalar component in the direction of OX. For F theta, I'm going to write minus 3 mu J2 mean equatorial radius of the Earth square over 2 R4, this time times sine square inclination and sine of 2 argument of latitude, like that. And finally for Fz, I'm going to write the same factor that multiplies my scalar component. That doesn't change. So 2R4. This time we have sine u times sine 2I, like that. Whew, it's been a lot of work. So the original goal was to analyze the effects of J2 on our orbital elements, because J2 being a perturbation, we know that the orbital elements won't be constant anymore. So the process started up by looking at the potential function of an oblate primary body. That was our UJ2 that we derived from first principle by considering that the order of our geopotential coefficient was held at 0, but that degree was varying between 0 and 2, and that's how we've discovered that was function of the constant J2, which is your 1.08, blah, blah, blah. And that gave us the potential function J2. Then we took the gradient of that to get the inertial acceleration due to this perturbing factor, J2. But we said, oh, that's not good enough, because what we want is FR, F theta, and Fz, and thus we looked at the inertial version of it in terms of vectorial equation and express all vectors in the orbital reference frame, played with the equation such that we ended up with one scalar multiplying OX, another scalar multiplying OY, and another scalar component multiplying OZ, and we called those FR, F theta, and Fz, obviously. So what would be the next logical step towards the evaluation of the effects of J2 on our orbital elements? Well, all we need to do is to look at the Gauss variational equations and simply plugging those expressions inside the Gauss variational equations to figure out the A dt, the E dt, the I dt, the rhan dt, the omega dt. But that would be a tedious process. So what we're going to do next time is to specifically look at the effects on rhan and the effects on the argument of perigee. And I'm going to do the work for only rhan, and I'm going to give you, we're going to do work only for rhan, and I'm going to give you the answer for argument of perigee, and the other three will end up being 0. That's good news for us. And then we're going to calculate the secular variation due to the effect of J2 on Rayan, and then look at the average rate of change as well. And then, as always, I'm going to talk about practical implications of having this perturbing acceleration affecting the motion of the spacecraft. And believe it or not, but there's an actual benefit of having this perturbing acceleration pushing and pulling our spacecraft around on orbit. But I'm going to save that for next time. I feel that that was a lot for one lecture in terms of deriving equations and playing with new stuff like Legendre polynomial and geopotential function, that double summation equation. Whew, that was a great deal of work we did today. So well done. Hope you're still following along, and I'll see you next time. See ya.